Well, don't look at the temperature variance, which is this plot. Look here. That you get 20% of the kinetic energy, the turbulent kinetic energy in the pipe, which is responsible of 80% of the thermal transport. So this, of course, is very interesting because it has been able to let us understand which kind of flow features are responsible of the thermal transport in this specific industrial problem, and suggest us a lot of possibility of eventually improving the design, eventually with vortex generators. Yes?
Correlation is not causation. So this is the Reichenbach principle, saying if X and Y are correlated, there's a common cause Z to X and Y. And so you seem to assume, so if we reduce X, then we reduce Y. And there has been an example, for instance, a mayor has learned that the number of firefighters is a correlation to the damage done by the fire. So he concluded if he abolishes the fire department, he would have less damage. So the fires in the city.
This is true, and I agree that one must be more cautious with such a conclusion. But in this case, in which the temperature is a passive scalar, and then the internal energy is being convected by the turbulent flow, I would say that it should be possible to confuse correlation and causality. I would do that. And well, in this case, I would really invite you to try this approach. This is why I have prepared a few Matlab lines. I didn't send yet to Miguel, I forgot it, but I will soon. So I will upload you a matrix, case 1, which is not a matrix, it's a little data set, which contains number of radial locations, number of theta locations, number of planes. I've given you a smaller data set so that you can run it on a laptop. The radial and tangential discretization, the mean temperature field, the mean velocity field, and then we have these U, V, W, and T. Can you see, no? Here. Snapshots, which are collected in R theta location times number of snapshots, which is the third direction. And the code is pretty simple. It's actually very few lines. So we have we first do the correlation matrix of U, V, and W. For computational cost, it's quicker to do like this. And then you get the correlation matrix of everything, summing the three correlation matrices. We also do the correlation matrix of the temperature. And then we project, after having done the singular value decomposition, we project all the quantities against the temporal modes. The tricky thing here is to build up the correlation matrix. Scott yesterday told you, and also Miguel repeated, but it is always worth to repeat it even a third time. Then when you build your correlation matrix, you are doing actually an integral over the area. So in this case, which is a case of a turbulent pipe, you want to have more resolution nearby the wall and less resolution in the center. And also here we have a cylindrical coordinate system, so the area value is not constant everywhere. So what happens is that I estimated the area corresponding to each point, which is d theta, which is 2 pi divided by the number of theta angles, times r, times dr. Dr was evaluated times as the mean of dr at n minus 1 and n minus 2. And of course, when you do the correlation matrix, since you want your sigma to be normalized, in order to have unitary integral of the spatial modes, we have to divide it by pi r square. Of course, in this case, the radius is equal to 1, so I have only divided the correlation matrix by pi. And this is everything very simple. Just we take our the snapshot matrices, we project it against the time coefficient, and we can run it. It takes very little, few seconds. Well, it should take few seconds, but now it's taking more than expected.
Maybe I can ask a question?
Yes, while we wait for the results.
So, I have a problem with an extended POD. Suppose you have your five odd wire sensors and you measure the velocity field.
Yes.
There are many mappings from the 5 hot wire sensors to an infinite dimensional velocity field and back to the 5, where the inverse is back to the 5 hot wire sensors, such that you have the identity if you believe in a linear relationship. Let's assume we have a linear relationship.
Yes.
And so what you are doing, you are choosing from the myriad of possible linear mappings, the one which minimizes the representation error with respect to your simultaneously sampled data. I could also take the least residual error. I could say, if I go from the pressure, from the hot wire sensors to the velocity field, I take the velocity field, only the velocity fields which are on average closest to the origin. So this would be the least energy based mapping, and you get quite different modes. And both of the modes, if you really believe that you have a control system, that essentially your velocity field is a kind of your actuation input which gives rise to the pressure field, then you should take the least energy mapping, and you get quite different modes. So we have elaborated this in the 2012 JFM by Michael Schlegel. So even if you believe in the linear relationships, there are a myriad of other possible modes which you can derive. And another thing, for instance, if you do control, the purpose of the control is essentially to destroy the attractors, so to destroy the ergodic properties, essentially also to destroy the linear mapping, which is the underlying basis of your extended POD with your representation error. So you would have also to adjust your linear mapping. So these are some words of warning.
Yes, I agree that the linear mapping is not the best choice ever. In this case, it was very nice because it was simple and it was working reasonably well.
And there are many linear mappings.
Yeah, but
there's not just the one. So you are choosing the linear mapping which minimizes the representation error of this particular say ergodic data set.
Yeah, this is why now we have moved to convolutional neural network, which eliminate the nonlinearity, and they also will minimize the reconstruction error again of this particular data set. What we do with neural networks, you can see the poster later, and we are reconstructing again employing the POD basis, and then in this case it is also optimal in the energy sense. This is why we prefer this option. So I got the results here. You can see the singular values of the temperature snapshot matrix and the turbulent kinetic energy, and we can plot also the extended values. One thing that is interesting is that the extended modes are not anymore ordered by their energy contents. So we have in blue the variance content of the temperature modes. In red, we have the variance content of the velocity modes obtained from the extended POD. In this case, the velocity modes are not anymore ordered by their variable content because they just obey to the optimality of the temperature reconstruction. And I can show you here also, if you want, the modes that will start appearing. So we have a temperature mode and the corresponding velocity mode for the first, the second, the third, and so on and so forth. Tell me, Bernd, you were asking... You're asking something? No? Okay. So are there any questions? Yes?
Ben, can I have the microphone? Exceptionally. Who has the question? Tomorrow you sit next to Ben.
Thank you again. Yeah, really interesting stuff. And what you've done seems intuitively great, you know? And the thing is, though, the first question I have is, did you try to compute the POD modes using both the temperature fluctuations and the velocity fluctuations with some kind of normalization? Did you ever try that?
I didn't try to do that, but it is something that intuitively I don't like it. Yeah. I don't like. Because they have different units, they have different magnitudes, and of course you can do a good normalization so that everything becomes non-dimensional and you put things together in a correlation matrix somehow. I was telling before there is a beautiful paper by Lumley who does this kind of analysis for a buoyancy-driven flow. And in that case, of course, you can relate density and kinetic energy, because the density will be multiplied by the gravity acceleration and by the multiplied by the gravity acceleration, and will return a sort of energy, and then you can multiply also the velocity square over 2 by the density, and you get a suitable scaling of the quantities. Here instead, since the temperature is a passive scalar, it was not really meaningful because it did not exist a composite quantity which could have been considered in this kind of problem. So it really depends on your analysis. Some people have done this to put together temperatures and velocities, but I doubt a bit about the optimality of the reconstruction, because you are reconstructing a composite quantity which I'm not sure that has a real physical meaning.
I agree with you. So my second question is, when you look at the turbulent heat flux calculation, where you have some integral, and I know you don't, in this case, integrate over time, but let's just say you integrate over time instead. Yeah. Your extended POD, if I'm not making a mistake of the understanding, will reduce to essentially the correlation of your spatial component for your original POD and the spatial component from your temperature. And of course you get a positive correlation because the modes look the same. But if they didn't look the same, then you would expect to get a very small correlation. The thing is, I don't understand.
So if in this case, don't confuse the two applications. In one case, we have a temperature field, we have done the POD, and we have projected the velocity snapshot matrix against the temporal basis of the temperature. In this case, you will get correlated with any temperature mode. You make sure that any velocity mode will contain all the amount of velocity which is correlated to this temperature mode. This does not mean that it will contain only correlated content, because again, the velocity matrix, the the temporal mode matrix has a unitary norm. So it is energy preserving. So if we would measure the temperature here and the color of the t-shirt of a girl which is passing outside of the building, we will not get at 0 because the noise will still be preserved. Okay? So you should make sure that you are correlating things which have a correlation. Yes?
May I offer another interpretation? I would say with so with extended POD, you are using another inner product. So instead of looking at the inner product you say, okay, your new inner product between, let's say, U and V equals, let's say, the temperature signal, simultaneous temperature signals, let's say, T and T prime. So you look at the effect of the velocity on the temperature. You can also do it the other way around.
Of course.
And this chain, if you assume they are linearly correlated, so if U equals C times T, in this case, you get a new inner product. And your extended POD essentially diagonalize and optimize the residual determined by your new inner product. So this is my interpretation of the least residual or extended POD.
This is correct.
What I was trying to formulate in my mind, actually. So,
and you can read our 2012 JFMs. We have tried to be better there.
Okay, good. The point is that I don't see why one method is wrong and one method is right, basically. You either say extended POD is right, in which case you can also change the inner product. You can make a mixture between different variables, or you say both is wrong.
Yeah, well, you can use everything, so there's nothing right and nothing wrong.
Thank you.
You can use everything and you can misuse everything.
Yeah.
And if you want to learn the art of the insult, you can use, you can read Sirovich's comment on the Aubrey model. So essentially what he wrote, so there was a rebuttal between both. And what Sirovich essentially said, the Aubrey model is just to prove that you can misuse the Gajokin projection.
Other questions? Yes.
I'm sorry, I'm going to lower the quality of the questions because I'm not an expert at all in this domain. But I was wondering, to be sure, so the example that you gave is a vertical pipe, and the test you did is on a horizontal pipe, correct?
No, it's well, we visualize it horizontal. We could visualize it vertical, but the temperature in this problem is a passive scalar, so we don't have buoyancy.
Okay.
So the gravity is not affecting the problem.
And if you would have to come back, let's say, to the physical problem or question that is related to the physical object that you have, so if you add this buoyancy, would you be able to reuse the work, the nice work that has been done, to extrapolate it or to correlate it to a more complex work?
So what I can tell you is that we have now some simulations with in which the temperature is modifying the viscosity, so it does not behave anymore as a passive scalar. It is not accounting for the effect of the gravity acceleration. It could be possible, but it might be important to verify the Rayleigh number in this case, and to check whether the buoyancy effects are relevant. What for sure is relevant is the variation of the viscosity, which will change then the structure of the boundary layer along the pipe tangential direction. In any case, I think these results are still meaningful because they provide us a lot of information in a simplified manner.
Thank you very much.
Yes.
When you were evaluating your extended POD, did you use in-sample error or out-sample error? So we've had a couple of examples where we had a couple of examples where the in-sample error was extremely
You're talking
good.
about this?
For instance, yes.
This is out of sample.
Wonderful.
Ah,
And beautiful talk.
thanks.
Do we have other questions? Maybe I have a very quick one. Based on everything you've learned about this beautiful test case, what will you do next? I mean,
So
in 10 years from now.
So
no, even in 2 months. I mean,
actually, I have to say something which is important before I close it, that all this was a good work done with Stefano and Marco, who is not here, and then the pipe simulation was done with these 3 guys on the right, and these people are those who have done with us all the experiment in Bologna. And now, if you're talking about the novel advancement, Alejandro, who is here, has done a nice poster on the use of a convolutional neural network to do the same stuff, and it works much better. And Bernd was suggesting k-nearest neighbors also. So I think that these tools with POD are very, very instructive, because nowadays, with the availability of more advanced machine learning tools, which you will see in the next day, you can get much, much more. But if you understand these simple tools, you can then have a lot of possibility of improving your data analysis. And so I think that we have a lot of opportunities, because POD is very good and very useful, but we can exploit more complex encoders and get even more interesting results.
thank you. I think then if there are no questions, we can close it like that. I will thank Professor Ianiro for this excellent lecture.
Thank you. Thank you.